Hello everyone, barely recognizable Schmeichel Phelps here, back to talk to you about parts of similar triangles. And I am getting a lot of Michael on the streets, and I want to make sure everyone knows that it's Schmeichel Phelps, okay? Who is Michael Phelps? That doesn't make any sense. I am the famous one.
First thing we're talking about is a median. That's a segment with endpoints being the vertex of a triangle and the midpoint of the opposite side. So in our example down here, you can see three separate examples of medians. Those would be segments that go from a vertex to the midpoint of the opposite side. So segment AN would be a median of triangle ABC because it goes from vertex A to the midpoint of the opposite side, point N. Same thing with segment BM. That would be a median of triangle ABC because it goes from vertex B to the midpoint of the opposite side, point M. And same thing with segment CP. That would be a median of triangle ABC because it goes from vertex C to the midpoint of the opposite side, point P. Now, an altitude would be a segment from the vertex to the line containing the opposite side and perpendicular to the line containing that side. So we typically refer to the altitude as the height of a triangle. And you can see this is what you're normally going to see. You have a segment going from a vertex that is perpendicular to the opposite side of the triangle. And that represents the height or altitude of this given triangle. So segment BD would be an altitude of triangle ABC here. Same thing with this segment right here. Segment BD is also an altitude of this triangle ABC because it goes from a vertex and is perpendicular to the line containing the opposite side. Now note that it doesn't have to be perpendicular to the side itself. Sometimes if you have an obtuse triangle, when you draw your altitude, the altitude is going to be perpendicular to the line containing that side. So if I were to continue this line AC beyond the triangle, segment BD would still be perpendicular to the line containing segment AC. Therefore, it still is an altitude. So that's what I need you to note here, is that an altitude can lie in the interior or exterior, or if it were a right triangle, it would be one of the sides of the triangle. Now, the triangle angle bisector theorem says an angle bisector in a triangle separates the opposite side into two segments that are proportional to the lengths of the other two sides. So what this means is that if we look at our example down here, we have a triangle CAB. If in this triangle you have an angle bisector, in this case ray AD, and that angle bisector crosses through or intersects the opposite side, so segment CB, it's going to divide that side into two separate segments, segment CD and segment BD. And the length of those two sides are going to be proportional to the other two sides of the triangle, meaning that I could set up a proportion where I have the measure of segment CD over the measure of segment BD is equal to the measure of segment CA over the measure of segment BA, just because ray AD is an angle bisector of this triangle. Now let's talk about some theorems for special segments of similar triangles. So the first one says, if two triangles are similar, the lengths of the corresponding altitudes are proportional to the lengths of the corresponding sides. So what this is saying just makes a lot of sense. If we know that two triangles are similar, like here we know triangle ABC is similar to triangle HFG, then we know the lengths of the corresponding sides have to be proportional. So the measure of segment AB over the measure of segment HF equals the measure of segment BC over the measure of segment FG, which equals the measure of segment AC over the measure of segment HG. All this is saying is that the length of the altitudes are also proportional to the corresponding sides. So the measure of segment BD over the measure of segment FJ is equal to the measure of segment AB over the measure of segment HF, which is equal to the measure of segment BC over the measure of segment FG, which is equal to the measure of segment AC over the measure of segment HG. Now, the second theorem for special segments in similar triangles says if two triangles are similar, the lengths of the corresponding angle bisectors are proportional to the lengths of the corresponding sides. So this is just saying the same thing we were just talking about in the first theorem, but this time it's with angle bisectors instead of altitudes. So we know that if these two triangles are similar triangles, then we know that the measure of the angle bisectors are going to be proportional to the lengths of the corresponding sides, meaning that the measure of segment BD over the measure of segment FJ has to equal the measure of segment AB over the measure of segment HF, which has to equal the measure of segment BC over the measure of segment FG, which has to equal the measure of segment AC over the measure of segment HG. Now, the third theorem for special segments in similar triangles says if two triangles are similar, then the lengths of the corresponding medians are proportional to the lengths of the corresponding sides. So this is saying the same thing that the previous two theorems were talking about, except this time we're talking about medians. So if we know that two triangles are similar, we know that triangle ABC is similar to triangle HFG, then the lengths of the corresponding medians, the segments that go from the vertex to the midpoint of the opposite side in each of the triangles, the lengths of those medians must be proportional to the lengths of the corresponding sides in each of the similar triangles. So the measure of segment BD over the measure of segment FJ has to equal the measure of segment AB over the measure of segment HF, which has to equal the measure of segment BC over the measure of segment FG, which has to equal the measure of segment AC over the measure of segment HG.
Now we're freestyling. It's example time.
Now, example 1 says given triangle ABC is similar to triangle HFG, we want to find x. So where's x in our figure down here? Well, it's right here. It's the measure of segment BD. Well, what do we know about segment BD? It looks to be an altitude of triangle ABC. Well, we know that these two triangles are similar, and we also know that these two triangles have a corresponding altitude. Segment BD corresponds to the altitude over here, segment FJ. Well, what do we know about the lengths of those two altitudes? Well, we know that they are proportional to the lengths of the corresponding sides based on one of the theorems we were just talking about. So we can set up a proportion to solve for x. We can say that the measure of segment BD, our altitude down here for triangle ABC, over the measure of segment FJ, the altitude for triangle HFG, has to equal a ratio of the corresponding sides. So which corresponding sides do we have? Well, we have the measure of segment BC and the measure of segment FG. We know that those are corresponding based on the similarity statement up here. So again, we're setting up our proportion. The measure of segment BD over the measure of segment FJ has to equal the measure of segment BC over the measure of segment FG. We can then plug in what each of those segment measures are equal to, and now we can solve for x. So how do we solve a proportion? We cross multiply. We use the cross product property. So we're going to multiply across and set the two products equal to one another. So 8 times 15, we're going to set equal to x times 12. We then solve for x by dividing both sides by 12, and we get x is equal to 10 inches. Make sure to use the correct units.
Tough for you to try.
Okay, doing the same thing here, except this time we're given that triangle XYZ is similar to triangle LMN, and we're trying to find the measure of segment ML. So where's segment ML? That would be right here, so we clearly need to find x. So how do we solve for x? Well, again, we're given two similar triangles, and we're given side lengths in those given triangles, so we probably need to set up a proportion. So we know that the measure of segment ML, based on our similarity statement, corresponds with the measure of segment YX. Okay, cool, we're given that, so we can go the measure of segment ML over the measure of segment YX. That has to equal, well, what other corresponding sides are we given? Well, we're not given any other corresponding sides, but we're given the corresponding altitudes. And we know that the lengths of the corresponding altitudes are proportional to the lengths of the corresponding sides. So we can set up a proportion where we have the measures of the altitudes, the measure of segment YW over the measure of segment MK, and set that equal to the measure of our corresponding side lengths, the measure of segment YX over the measure of segment ML. Now we can substitute in the measures of those given segments, and we can solve for x. Perfect. So how do we solve a proportion? We need to cross multiply. We got to use the cross product property. So we're going to multiply across and set the two products equal to one another. So we're going to multiply 6 times the quantity for x minus 12 and 9 times 11. Now 9 times 11 is just 99, but 6 times the quantity for x minus 12, we have to distribute the 6 to the 4x and to the negative 12. Now we can solve for x by adding 72 to both sides, dividing both sides by 24, and we get x is equal to 7.125. Now we're not done. This is not what we were trying to find. We're trying to find the measure of segment ML. And the measure of segment ML is 4x minus 12 feet. So we take that x that we found, plug it in for the measure of segment ML for x, and we simplify. 4 times 7.125 minus 12 is going to give you 16.5 feet. Now, example 2 says given triangle ABC up here is similar to triangle HFG down here, we want to find the measure of segment FJ here. So in order to find the measure of segment FJ, we clearly have to find y, meaning we have to set up an equation in order to solve for y. So how do we set up that equation? What do we know about segment FJ? Well, it goes from a vertex to a point on the opposite side that lies directly between the other two vertices. Because we know that the measure of segment HJ is equal to the measure of segment JG, we know that these two segments must be congruent to one another, meaning that point J is the midpoint of this side. And because segment FJ goes from a vertex to the midpoint of the opposite side, we know it must be a median of triangle HFG. Now, how does that help us? Well, we know that triangle HFG is similar to triangle ABC up here. And we know that segment BD right here goes from a vertex to the midpoint of the opposite side as well, meaning that it would also be a median of this triangle up here. And because triangle ABC is similar to triangle HFG, we know that segment BD, this median, must correspond with segment FJ, this median down here. And based on the theorems we talked about earlier, if two triangles are similar, the lengths of the corresponding medians are proportional to the lengths of the corresponding sides. So all we have to do is set up a proportion based on the lengths of the corresponding medians and the lengths of the corresponding sides, and we can solve for y. So how do we set up that proportion? Well, we set the lengths of the corresponding medians, so the measure of segment BD over the measure of segment FJ, are proportional to the lengths of the corresponding sides, so segment AC over segment HG. Now, we can plug in what each of those measures are equal to. The measure of segment BD is 10 meters, that goes in here. Measure of segment FJ is 3y minus 4 meters, that goes in here. Measure of segment AC, oh, what's that? Well, it's going to be 7.5 meters plus 7.5 meters, so that's 15 meters. And then the measure of HG is going to be 6 meters plus 6 meters, which is 12 meters. We now have a proportion that we can solve using the cross product property. So we're going to multiply across and set those two products equal to one another and solve for y. So I take 10, multiply it to this 12, and I get 120. Set that equal to the quantity 3y minus 4 times 15. Now, when you multiply this quantity times 15, you need to make sure to distribute that 15 to the 3y and to the negative 4. You can then solve for y by adding 60 to both sides, dividing both sides by 45, you get y is equal to 4. But we're not done. We're trying to find the measure of segment FJ. So how do you find the measure of segment FJ? You take what you found for y, plug it in for the measure of segment FJ, which is 3y minus 4, and then simplify. 3 times 4 is 12, minus 4 is 8. Therefore, the measure of segment FJ is 8 meters.
Time to go for the bronze. You try.
Okay, doing the same thing here, except this time we know triangle JKL is similar to triangle PQR down here, and we want to find the measure of segment KM. And you see that in order to find the measure of segment KM, we clearly have to find Z, so we got to set up an equation in order to solve for Z. So what do we know about segment KM? Well, it goes from a vertex to the midpoint of the opposite side. Therefore, segment KM would be a median of triangle JKL. We also see in our similar triangle down here, we have a segment QS, that goes from a vertex to the midpoint of the opposite side, making it a median as well, only this time in triangle PQR. Now, based on our similarity statement and these two figures, you see that segment KM, the median in this triangle, corresponds to segment QS, the median in this triangle. And because these two triangles are similar, we know that the lengths of the corresponding medians are proportional to the lengths of the corresponding sides. So we can set up a proportion in order to solve for Z. So how do we set up this proportion? Well, we're going to go the measure of segment KM, the median up here, over the measure of segment QS, the median down here, is equal to the measure of segment JK up here over, which segment does segment JK correspond to? Well, if you're not sure, you can always check your similarity statement. The measure of segment JK corresponds to the measure of segment PQ. Now we can plug in what each of those things are equal to in our proportion over here, and we can solve for Z. So how do we solve a proportion? We use the cross product property. We're going to cross multiply, set the two products equal to one another, and solve for Z. So I take the quantity 8z minus 5, multiply it to 6, and take the quantity z plus 9, multiply that to 23. Now, anytime you're multiplying a quantity by a constant, you need to distribute. So we got to distribute the 6 to the 8z and to the negative 5. You also have to distribute the 23 to the z and to the 9. We can then solve for z by subtracting 23z on both sides and adding 30 to both sides. We then divide both sides by 25, and we get z is equal to 9.48. But we're not done. We want to find the measure of segment KM. So we take what the measure of segment KM was equal to, plug in what we found for z, and we simplify. 8 times 9.48 minus 5 gives you 70.84 yards. Now, example 3 says solve for the given variable. So here we have triangle ABC, and we have segment BD, which appears to be an angle bisector. It bisects angle ABC. So we're clearly going to have to use that information in order to solve for x. So how do we set up an equation in order to solve for x? Well, since we know that segment BD is an angle bisector of triangle ABC, we can use the triangle angle bisector theorem, which says an angle bisector in a triangle, segment BD, separates the opposite side into two segments, segment segment AD and segment CD, that are proportional to the other two sides of the triangle, segment AB and segment BC. So what we can do is set up that proportion and solve for x. We can say that the measure of segment AD over the measure of segment CD has to equal the measure of segment AB over the measure of segment BC. We can then plug in what each of those things are equal to. The measure of segment AB is 15, that goes in there. The measure of segment BC is 27, that goes in there. The measure of segment CD is x, that goes in there. And the measure of segment AD, oh, we don't know that. Well, we do know that the measure of segment AC, this whole side, is 27. We know that the measure of segment CD has to be x, therefore the measure of segment AD would just be the whole thing, 28, minus whatever the measure of segment CD is, x. So 28 minus x is what we're going to put for the measure of segment AD. So we can plug that in there. Now we have a proportion that we can solve for x. So how do we solve this for x? We cross multiply. We use the cross product property, cross multiply, and set the two products equal to one another and solve for x. So we take the quantity 28 minus x, multiply it to 27, and then we take x and multiply it to 15. Now when you multiply 27 times the quantity, 28 minus x, you have to distribute the 27 to the 28 and to the negative x. You can then solve for x by adding 27x to both sides, dividing both sides by 42, you get x is equal to 18, and you're done.
Schmeichel Phelps says it's okay to be mediocre. You try.
Okay, we again have an angle bisector in our triangle, so we can use the triangle angle bisector theorem to again set up a proportion and solve for our given variable here, x. So how does that work? Well, this angle bisector separates the opposite side here into two segments that are proportional to the other two sides of the triangle. So we can say that 7x over 2x plus 8 has to equal 10 over 14. Now all we have to do to solve this proportion is cross multiply, set the two products equal to one another, and solve for x. So I'm going to take 7x, multiply it to 14, then I'm going to take the quantity 2x plus 8 and multiply it to 10. Because you're multiplying the quantity 2x plus 8 to 10, you have to distribute the 10 to the 2x and to the 8. We can then solve for x by subtracting 20x on both sides, dividing both sides by 78, and we get that x is approximately equal to 1.026. Please note that we had to round to the nearest thousandth, which is 3 decimal places. Now example 4 says given segment FD is parallel to segment BC, segment BF is parallel to segment CD, and segment AC bisects angle BCD, we want to prove that the measure of segment DE over the measure of segment EC is equal to the measure of segment BA over the measure of segment AC. Now the first step in a geometric proof is to mark up the figure with the given information. What are we given? We're given that segment FD is parallel to segment BC, so we mark that up that way. We're also given that the measure of segment BF is parallel to segment CD. Lastly, we're given that segment AC bisects angle BCD. That will come in handy, but we're not going to mark that up yet because it doesn't say angle something is congruent to angle something. So we'll use that later on. So we can move on to the next step in a geometric proof, the second step, which is to state the given. So the given is that segment FD is parallel to segment BC, segment BF is parallel to segment CD, and segment AC bisects angle BCD. The reason for that, it's given. Step 3 in a geometric proof, come up with a game plan. How are we going to get from what we're given to what we're trying to prove? Well, what am I trying to prove again? I'm trying to prove that the measure of segment DE over the measure of segment EC is equal to the measure of segment BA over the measure of segment AC. So the way I could show that is if this small triangle over here was similar to this big triangle, then I could say that the corresponding sides of those two triangles must be proportional to one another. So that's how I'm going to have to do this. I have to show that triangle DEC is similar to triangle BAC. So how do I do that? Well, we can start with segment AC bisects angle BCD, meaning that angle BCE has to be congruent to angle DCE by the definition of angle bisector. We also know that this segment right here, segment BC, is parallel to segment FE. That's also given. Because of that, we could look at these two parallel lines and look at segment AC as our transversal, meaning that this angle right here and this angle, angle DEC, would be alternate interior angles. Therefore, they would be congruent to one another. We also have these two pair of parallel lines, segment BA and segment CD. If we look at segment AC again as our transversal to those two parallel lines, we see that this angle, angle DCE, is an alternate interior angle with angle BAC. So those would be congruent by the alternate interior angles theorem. Now we have shown that two angles in this small triangle are congruent to the corresponding two angles in the big triangle. Therefore, the two triangles would have to be congruent by the angle angle similarity postulate, meaning that their corresponding sides must be proportional to one another. That's how we're going to do this. So we'll go through it again just in case you missed it. First, we said that because segment AC bisects angle BCD, that these two angles right here must be congruent to each other by the definition of angle bisector. We then know that because these two lines are parallel and cut by a transversal, that these two alternate interior angles must be congruent. Same thing over here with these two parallel lines cut by this transversal. These two alternate interior angles must be congruent as well by the alternate interior angles theorem. Now we've shown that two angles in one triangle are congruent to the corresponding two angles in the other triangle. Therefore, these two triangles, triangle DEC and triangle BAC, must be similar to one another by the angle-angle similarity postulate. Now, because the two triangles are similar, we can say that their corresponding sides must be proportional to one another by the definition of similar triangles. Anytime you have similar triangles, you know that the corresponding angles are going to be congruent and the corresponding sides are going to be proportional.